Hello, thank you very much for being here. 90% of the world's data was created in the last 2 years, and we expect this volume of data to double in size every 2 years. This dramatic data growth has prompted the creation of core infrastructure and specialized roles around it to manage it, resulting in a vast ecosystem of tools and roles like data analysts, data scientists, data architects, or data engineers, to mention a few. Still, there are new challenges as every day the speed, volume, and complexity of this data keeps growing. All these challenges are well suited for a programming language like Go. As we know, Go has the speed, safety, and reliability of a static language while providing the productivity of a dynamic one. But let me tell you something. Out of all the programming languages in this ecosystem, Go is almost nowhere to be found. Does it even have a role to play? Welcome, everyone, and thank you for coming here today. I'm honored to talk to you about the intersection of Go and data engineering. Today, we'll explore the challenges and learnings of introducing Go to data engineering, an established domain with well-known technologies. And also, you will see how Go is helping transform our data operation and grow our data engineering organization. My name is Juan Brandao. I'm from Panama. I'm a data engineering director at Procter & Gamble. I've spent my career moving data around. I've had any imaginable data role, and today I find passion bringing best practices from domains like software engineering into the data community. So let's start with why do we need data engineer? We need data analysts to extract the insights and provide recommendations so organizations can act on them. We need data scientists as they are the ones that build the machine learning models that power the recommendation, prediction, classification systems that modern applications use today to improve our experiences and understanding of the world. Now, the transactional systems that typically generate this data were not designed with these use cases in mind. Many, if not all applications, store the current state of entities, while analytics and machine learning is concerned not only with the current state of entities, but the history of a state an entity has gone through. Data engineers create the processes and infrastructure to preserve, curate, and serve that data state evolution in an accessible way for the end users. But how do we do data engineering? To achieve these goals, data needs to be ingested from the source system where it's created. It needs to be transformed, as the native data model typically is optimized for transactions. It must be clean, standardized, and shaped into a data model its users can easily consume. It also needs to be served into a platform where its user can access it easily and securely. Across all of that, we need a storage to store the intermediate representations of data until it takes its final shape. And given the expectations put on these systems today, we have standard practices embedded in the lifecycle, including operations, architecture, data management, security, and software engineering. All these buckets have a huge list of tools available that comprise the data engineer's toolbox. But where do data engineers come from? Data engineering is a relatively young field. By 2012, the Harvard Business Review was naming data science as the sexiest job of the 21st century. By that time, only a handful of organizations understood that to do data science at scale, you were going to require specialized roles around it, like the data engineers or machine learning engineers that we know today. With this, data engineers may come from different backgrounds. Some may transition from software engineering. They may come from an unrelated background. They may come fresh from university or transition from an adjacent area like data analysis or data science, as I did. Given the high demand for these roles, it's pretty common for data analysts and data scientists to transition into it. When you don't have data engineers in your team, you need to develop skills to extract and transform data. But so far, that's just the mean to an end. Have a clean data set to start what we call the real work. The positive on this path of transition is that we know what our users want. The not so positive is that many times we build our foundation in throwaway code. One-off data processing script trying to get to the good parts. Without software engineering, architecture, or data management best practices in our belt, we're not exposed to key system design principles or healthy coding practices. Over time and with dedication, we improve. But when you have the task to grow an organization with quality, accelerating growth with quality is the part where Go has become an ally. Let's see a little bit of the context where we do data engineering. Procter & Gamble is a consumer packaged goods company. Our brands are trusted in millions of kitchens, laundry rooms, and bathrooms around the world. We are committed to making people's life better in small but meaningful ways every day. We operate in around 70 countries, and our products are sold in more than 170 countries. I live and work in Latin America, leading its data engineering organization. Latin America is a fast-growing region, with a population of around 650 million people in more than 20 countries. As you see, our products are physical. We're talking about shampoo and detergent. We have to reach consumers that shop from the big retail chains to small store formats in the farthest areas of the region. Thus, the data for our operation is not only generated by our internal systems or the product's usage. The scope of our data teams are all areas that impact the consumer experience, like advertisement and media vehicles, retail execution, logistics, IoT, and much more. To have data visibility in some of these spaces, we must rely on partners that record the product's state on the ground, on the shelves. As some of our internal data products require this external data, we have two types of data sources. One that we call standard, which have very mature interfaces to serve data, like the online advertisement platforms. No challenges there. But we have what we call the non-standard data sources. These are the partners that gather measurements of the product on the ground, among others, and they are different by country for the same data type. This data diversity makes it difficult to scale. For this reason, the products have developed their own ingestion pipelines, leaving little room for reuse, pushing the complexity of data ingestion to the products, which then diverts focus from the core features. We decided to take over the data ingestion process centrally to improve reuse and the quality guarantees. We named this system the First Mile Data Service. Now we had to implement a platform where we could interface with multiple data sources, codify data contracts at scale, provide guarantees on data like accuracy, availability, and timeliness, and publish data to an internal data product through a consistent interface. There were few out-of-the-box solutions that could help in this context. Nothing required less or equal effort to set up versus building our own solution. Having decided to build, we had to pick a programming language among many other decisions. The team was solely proficient in Python, the obvious option, as it always is for almost any data engineer. But in the past, we've had challenges with efficiency, scaling, and maintaining Python code for similar projects. We needed a language that could help us scale reliably, could help us make type-safe guarantees on data, that has fast iteration cycles, and that could allow us to add abstractions only when needed, as we never know what new challenges the next data source could throw at us. Spoiler alert, we chose Go. I like to say from here that everything was just party and fun, but aside from a couple of us, no one in the team or the company probably had experience building services in Go, so we had some roadblocks to overcome. First, There are different data sources per country for the same data type as mentioned. The predominant interface are REST APIs, but there are many different authentication, query, and resource patterns, and on top of that, different data models and data contracts. Second, we had to introduce a new language to the company and data engineering. No other project internally was using Go, and with that comes lack of internal tooling and support. Third, ramping up a team with only Python proficiency. We needed to learn the language and master the toolchain. But not all the hope was lost. For the challenge of diversity of sources, this is part of why we decided to tackle the data ingestion challenge centrally. Go helped us abstract the details of each data source, making processing at scale robust, efficient, and observable. This is a little overview of the first mile data service. We have clients for each data source, which is demanding but needed. We have what we call a caller, which knows how to call all the clients. It's the part that generalizes the abstraction, and the pattern goes around requesting a resource for a given period and a set of parameters. We have the syncer, which keeps the target storage in sync with data available at the data sources. It dispatches any request to any source through the caller. And finally, the lawyer. This is an extra layer of observability to monitor the data contracts. I love to talk more on the design, but this talk is more about the impact of Go in our area. On the second roadblock, making a case for Go. First, we started with the small data-driven wins. The first mile data service was our first big project in Go, not the first one. We had a previous challenge to serialize and load a billion entities into a platform. With optimized Python, it would take 15 days. We did a proof of concept in Go, and out of the box, without concurrency, the same took 1 day. With this, we show that Go is great for fast serialization and type safety, the type of requirements required for the first mile data service. And also we show that it was faster to bring to production, as building and running a binary compiling Go doesn't require a specific interpreter or a virtual machine in your environment. This gave us the confidence to use Go in bigger projects. The takeaway here was to have data to validate your assumptions, and if not, build something and gather data. On the same challenge, we also had to build our own tooling. But the Go ecosystem is mature. Today, we have a fraction of CI/CD infrastructure versus other languages internally. And we also built some tools to interface with the rest of the data engineering stack. For example, we developed a Go to Spark schema generator. This helps us to provide type safety guarantees across the data lifecycle when handing over data ingested using the first mile data service to Spark processing pipelines downstream. The takeaway here is that all the tooling may not be available, but don't be afraid to go beyond. And on ramping up a team with only Python proficiency, we had to support our team and align on clear goals. The most important and beautiful challenge is dealing with ourselves, humans. So from day zero, we make clear that the goal isn't and will not be to replace Python. The goal is to complement the data engineers ecosystem. Stating this upfront helped ease concern and approach Go with the right mindset. Also, all our engineers have a similar background, which is good. They understand each other, but this adds low technical diversity. And in a Python-only ecosystem, you actually don't need to be exposed to any other language. But you end up missing an important comparison point. Learning another language helped to level the playing field. What else helped to onboard them? Having senior engineers learn and guide the rest. Code reviews and pair programming became excellent tools for immediate feedback. Now, the consequences of adopting Go. The following may be evident to you, but it's insightful to see what impresses an engineer when they are introduced to Go for the first time, as we all were once. To be fair, I will use Python for some comparisons because Python is the data engineer's lingua franca. But this is not a matter of one versus the other. As with any tool, each one has pros and cons and a job to do. Trying to see which one is better is like deciding on the best ice cream flavor. On error handling. In Python, error handling can be an afterthought. In Go, it's what I call a before thought. By design, you're forced to deal with errors, and you get to know about them right from the function signatures. The frequent error handling in Go, the small friction it adds, starts to shift the engineer's mindset. So when they are writing Python Go and that friction is not there anymore, they feel that something important is missing, and it is. It now makes them pay more attention to error management in Python because it's part of Go flow. And even in simple examples like this one, converting a string to an integer, it may be simple but a highly recurrent operation in data engineering that can fail. And with this, my unpopular opinion, if R is not equal to nil, it's a gift. It may feel tiring sometimes, and we may have a more ergonomic error handling pattern in future revisions of the language. But being told explicitly that your function can fail as part of its signature is an underrated gift, especially when you come from languages with exceptions or error handling strategies that don't make it evident, not even in the documentation. Now, overall, we are getting a more robust and reliable system in any code base. The type system as documentation. Function signatures clarify what types are expected and returned. This helps make the official Go documentation our go-to place to answer questions. Following this, engineers started to see their programs were consistently correct, compiling, running, and doing what they were expecting on the first tries. Before, the engineers also mostly did the Python's typing annotations because our CI/CD pipelines enforced them. Now, they see the value in safety, documentation, and maintainability that types bring. And we notice because they are using them even in prototyping code. With all of this, we saw collectively that the ratio of trips to Stack Overflow per lines of code decreased as well, assuming this was an official metric of productivity. The type system for the data types. Go forces you to think about data types and strictly defined schemas, with the benefit of moving many errors from runtime errors to compile time errors, which is important when you're building mission-critical infrastructure. As in this example, getting a key from a JSON literal is a one-liner in Python. In Go, you first need to create a type. Then, after marshalling it, still you need to handle the error. This is annoying, right? But this is the type of annoyances that makes our system robust and our team happy. And on testing Go are just code. There's one way to do it, and you have all you need to start right away immediately. Using interfaces not only helped us decouple our code, it made it easier to test. This was mind-blowing. On top of that, table-driven test made trivial to test the happy path, but even more trivial to test the sad path. Benchmarking and examples as part of the test suite was another mind-blowing. The team now is more confident in testing and has learned essential techniques across. What else the team didn't expect? That publishing a package almost just required having a version control repository. In contrast, many of them haven't published yet a Python package. Dependency management is awesome. And I mean, even before, just installing and running a specific Go version is trivial. No need to manage custom environments. The Godot tool has helped grow a culture of documentation in the team as we get instantly rewarded. And GoFont saves a lot of time, not only reading, but writing and reading code, as all the code base now looks familiar, looks the same. The health of our Go code base is a reason for pride and is driving the quality of the rest of the code bases. What I didn't expect, I hope the team to learn from adding Go to their toolbox, but it went up to engineers expressing in career conversations that they want to keep working with Go in the next role, they want to become experts in Go, and that they want to grow the company's Go community. It was fantastic. In summary, we've explored what data engineers are, what they do, and how their toolbox looks. We've seen that Go is explicitly absent from the data engineer's toolbox. Imagine you become a better master in your craft overall just by adding a specific tool to your toolbox. That's what we found in Go. The value that Go adds to the data engineer's ecosystem overshadows the challenges associated with introducing it. Finally, we are starting to solve Go integration with the data engineer's toolbox in the periphery of data processing engines. While some tools like Beam and Kafka already provide native or close support for Go, and we see more coming every day, we can still ask ourselves, is Go missing in the data engineer's toolbox? For our team, it was. Will Go become broadly adopted in data engineering? Well, this journey is just starting. We arrived at Go for the speed, safety, and reliability, but we are staging because it's making us better engineers every day. Thank you very much for your time today. It's been an honor.